Thank you.
Yeah, no, I'll stable it. Thank you. All right, so with these rules, on example number 1, the natural log of 2x is going to be, well, who thinks they can do it already? Steven. Mm-hmm. Good. Sorry, I just did not have that on the screen. So, natural log of whatever is 1 over that, times the derivative of what's inside, so times 2, and then the 2's cancel, and you just get 1 over x. Okay? Thoughts on how we're going to organize the second one, Michelle? What rule are you going to apply? Product. So go ahead and start that process. Can you tell me what's going to be? So what does your product rule look like, Michelle? So that's your first times your derivative of the second. Good? Perfect. So that's all just going to be 1 plus the natural log of x. Simple? Okay. In this next exercise, I'm kind of going to have us do 2 and compare them because they're different. Same kind of the same thing I pointed out with sines and cosines yesterday. On this one, the whole thing is being cubed. So what rule, Nathan, would I apply first? Nathan Z.
The
Power. So tell me what to write.
3 times ln of x squared
Mm-hmm.
times 1 over x.
Perfect. So all things considered, this will just be 3 times the natural log of x squared over x when you condense that. Versus, on the other one, the x is actually being cubed. You don't need parentheses here, but if it helps you see it, you can put them there. That cubed is on the x. So your derivative for this one, oh, take a stab at it, Stephanie. Okay, so this one holistically was a power rule first. This one holistically is a natural log problem. So the derivative of a natural log is what? Okay, but this is not an x, this is an x cubed. So we are going to start with 1 over x cubed, and then what do we have to multiply that by? Because of the chain rule. So do you see the difference between the kind of the, it's not a paragraph, but the parent rule, ln of x, I just went over that. That's when what's inside is just a plain old x, so we don't need the chain rule. What's inside here is an x cubed. So we now need the derivative of what's inside. So the derivative of x cubed is 3x squared. So this ends up being your x squared is going to cancel with 2 of the 3 from the bottom, and you just end up with 3 over x. Jaylee.
Why don't you have to do the thing again, like the 3x, and then do times 2x? Or times 6? Like take the derivative of the inside of the inside.
So the derivative of the natural log is 1 over x cubed, and then it's just times the derivative of what's inside. The derivative of x cubed is just 3x squared.
But then, why do you sometimes then take the derivative of what's inside that?
What's inside of that is just x, so the derivative would just be 1. So
3x squared.
inside the 3x squared is like x squared. So
Okay, so let me change up a problem to maybe highlight what I think you're... So if I do the natural log of 4x cubed, like this one would have a second layer of the chain rule. Okay, what's inside of here is just a function, x cubed, which has a derivative of 3x squared. So on this one, when you take the derivative of what's inside is just x cubed. So the derivative of that is just 3x squared. Here, the derivative of what's inside would be, there's a function within the function. So it would be bringing the 3 out in front of 4x squared times the derivative of what's inside of that, which would be a 4. Here, you would never, this is the derivative of what's inside. You never take the derivative of a derivative. This is already the derivative of what's inside. So you're trying to double layer taking the derivative of the derivative, versus this one is taking the derivative. So I'll do 1 over natural log of, 1 over 4x cubed times the derivative of what's inside of this is a power rule, but there's a function within that, so then it's times the derivative of what was inside of that. It's not the derivative of the derivative again. Josh? You look angry.
No.
Okay. All right, so I think we're done here. So look how different those look, by the way. The original functions were only slightly off, but the derivatives look quite different. All right. Now this one, first and foremost, is a natural log question. So our derivative is going to start with 1 over this. Well, we can change it later. We'll worry about that later. So it's 1 over this, but times the derivative of what's inside. So the derivative of cosecant x. What's the derivative of cosecant? Negative cosecant, no, cotangent. Negative cosecant x, cotangent x.
Why wouldn't you do it?
So why change that cosecant early? Because now your life is actually going to be even easier than that, and those will just cancel. Stephen?
They went ahead and I did as a product rule. That doesn't work. Yeah, that's
Product of what times what?
ln times.
ln doesn't float on its own.
Oh yeah, that's right.
If it was the ln of x times an absolute value, maybe. But we don't have a shortcut for the derivative of an absolute value function on its own. Look at our list here. Not once do we have the derivative of an absolute value function on its own. Actually, we do, but we haven't learned it yet. So don't pretend like we have that. We don't actually know that yet. Okay? So right now, the absolute value that's involved here is a natural log one, which actually isn't even on this page, which is kind of funny. We're doing this one today, and also the natural log of the absolute value of u. So anyway, once we're here, the cosecants cancel, and we just have negative cotangent of x. So on the back side, I threw a quotient rule at you. So h prime of t is the bottom, t, times the derivative of the top, 1 over t, minus the top, times the derivative of the bottom, all over bottom squared. So this t and t cancel, making it 1 minus the natural log of t over t squared. No chain rule there because it's all just t's. Okay. Why did I write use properties? Well, I'll remember once we get into this why I might have written that. So the first thing I'm going to do is change this cubed root to x minus 2 over x plus 2 cubed. 1/3. Oh, I think I know why I did it. Why don't you try this? I think we're going to have better understanding if we kind of try something, and then I think I'll show you what I meant by that. Steal a couple. You three were the easiest targets, I'm sorry.
Yeah.
Okay, oh boy. I'm going to start with this one because there's the least amount there, so I'm the least confused. All right, so rewrote it. So what rule did this one follow first? Power, which is incorrect, right? The whole log is not being raised to the 1/3 power, is it? It's just this piece. Yes? So it should have first been 1 over this. And then we'll get times the derivative of what's inside. So there's that back. Connor, can you pass that forward so it gets back to its owner? Okay, this person did start with the natural log first. So they did 1 over that piece times the derivative of what's inside. So this is what was inside. So they brought the 1/3 out in front, left the fraction alone, raised to the negative 2/3 power, times the derivative of what's inside of that, which is this. I don't know where this is coming from. Yeah, so you did the bottom times the derivative of the top minus the top times derivative of the bottom. Oh, you did it as a side project. Good. Okay, so bottom times derivative of the top minus top times derivative of the bottom all over bottom squared. So x plus 2 minus x minus 2. Should the x minus x cancels? 2 minus negative 2, that's where the 4 came from. Awesome. Over x plus 2 squared. Oh, great. So then from here, where did we go? Oh, this is x minus 2 over x plus 2 to the negative 1/3 power, isn't it? Right? Because this is on the denominator with a positive 1/3 exponent, you could bring this up as x minus 2 over x plus 2 to the negative 1/3 power. The reason I like that is because now I have a common base, x minus 2 over x plus 2 to the negative 2/3 power. So this and this would just become that to the negative first power when you add the exponents. Do you follow? Michelle's giving me a nod. What's that? This 1/3 here? Oh, I'm not there yet. I'm just talking about these two. Will essentially become this to the negative first power. And when you raise a fraction to the negative first power, it just reciprocates it. So all of that would just be x plus 2 over x minus 2. Yes, the 1/3 is out in front, and this is just 4 over x plus 2 squared. So that one and that one will this one will cancel with one of those. So it'll just be 4 over 3 times x minus 2. What a cinch. I'm just kidding.
I was close.
Here, just don't worry about furiously copying that down. Here's what I meant by using the properties. Logs have their own set of properties. Connor, can you take that back and send those back to their respective owners? Logs have their own properties, yes? When you take the log of something that's being squared or raised to a power, where can that power go? Right? Think about log base 5 of x squared. Where does that go? Out in front. And that's just a way of rewriting the original function, not to be confused with the power rule. So still, this is the original function. Haven't started taking the derivative yet. Yes? That's a log property. Bringing the exponent out in front, not to be confused with having started the power rule first. So if you do it this way, it's going to be so much easier. Right. So now I just start my derivative. I'm going to call this f of x equals. So now I'm about to start my derivative. It'll be 1/3. And then the derivative of the natural log is just 1 over x minus 2 over x plus 2. So we're still going to have a chain rule, but I don't think it's going to be as complicated. By the way, this 1 over this fraction, well, let me finish this out first. So there's my 1/3, and doing my natural log derivative times the derivative of what's inside. So that was the quotient rule, which, Lily, was that your paper? Can you just hurry me up on that quotient? Okay. So when you do that, it's just 1/3. 1 over a fraction just reciprocates the fraction, so that would be just x plus 2 over x minus 2 times 4 over x plus 2 squared, and we get the same piece there. Follow? So with this natural log and logs in general, we haven't done the derivative of logs yet. This is specifically only natural logs today. But keep in mind, if you have an exponent, you can avoid that power rule piece just by bringing it out in front to rewrite it based on your log properties. Okay? Evaluating the derivative, there's nothing special about this. It's just an application. So we would find the derivative first. That's nothing crazy. And then just plug in a pi over 2 to evaluate it. And then the last one here, finding an equation of the tangent line to the graph. Again, equation of a tangent line, we need a slope and a point. So to start this, we want to find, oh, I didn't give you the point. I have to give you the point. So let me see what I forgot here. Find an equation of the tangent line. I stole this one. Okay, the point was 1, 2. So, for writing the equation of a tangent line, we already have the point. We just now need to evaluate the derivative at 1 to get our slope. So, it's still the guts of this problem are still finding the derivative. So, y prime equals the derivative of e to the something is still e to the something, so this is still going to be 2e to the 1 minus x squared, but then we're going to have to multiply it by the derivative of what's inside, which is negative 2x. So this all becomes negative 4x e to the 1 minus x squared. So now when we evaluate this at 1, our slope is going to be negative 4 times 1 times e to the 1 minus 1 squared, which is e to the 0 power, which is 1 times negative 4 is negative 4, and then you write the equation of your tangent line. Y minus 2, negative 4, x minus 1. And then the confirm on the calculator is just a nice little, oh, isn't that lovely kind of situation. So you draw your function, plot your line. Isn't it lovely? Okie doke. So, not overly crazy today. We learned a new rule, and we learned about how that can make it quicker by following the log rules. That's just one thing to keep in mind that will speed up your life.
How are we gonna finish the